Hi, everybody. So today I'd like to introduce our speaker, Grant Linley, postdoc working at WildObs here at UQ. He will be discussing the impact of the 2019-20 wildfires on terrestrial species in southeastern Australia. But before we get started, I'd like to do an acknowledgement of country. The University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to the country. We recognize their valuable contributions to Australian and global society. With that, I'll let Grant take over.
Thank you. Good morning. Thank you for coming on to my talk. I would like to pay my respects and acknowledge the Wiradjuri, Chettamatan and Waveroo people as the traditional custodians of the area where the research took place. Today, I'm going to talk to you about what I did during my PhD, what led us to ask the questions that we asked, what we found, and briefly, a little bit about where I'm heading next for some of the follow-up questions. Climate change is exacerbating wildfire conditions globally. The frequency of extreme wildfire events in the 99.99 percentile increased by 2.2 times between 2003 and 2023. While global burn area is declining, fire behaviour is worsening, especially in boreal and temperate conifer biomes. Changes in the frequency and intensity of extreme wildfires has implications for carbon storage, human exposure to wildlife disasters, and can impact flora and fauna, especially where fires are uncommon. The 2019-2020 wildfires were unprecedented in scale and severity, burning over 10 million hectares of forest, with a record 1.8 million hectares burned at high severity. Shown here on the map in red is the extent of those wildfires across Australia. These wildfires impacted 832 native vertebrate species and burnt the habitat of over 17,000 plant species. This offered an opportunity to understand how species respond to wildfires of this magnitude. In a recent Nature paper that I was part of, we looked at the impact of the 2019-2020 wildfires on flora and fauna across much of the fire footprint. We found that the largest effects of on flora and fauna were in areas with frequent or recent past fires. In addition, areas that burnt at high severity outside of protected areas or under extreme drought also had larger effects. However, while this answers the broad question as to what drives the impacts of these wildfires, the research that I did during my PhD goes further than this by looking at the effects of the extent of fire severity, behavioural responses to wildfire, and the role of refuge to reveal resilience mechanisms across the fire-impacted ecosystems. This is an overview of what I did during my PhD. I defined megafire, looked at the impact of wildfire at a landscape and site scale, and investigated the role of common wombat burrows in post-fire ecosystems. Following the 2019-2020 wildfires, a flurry of research was published examining the effects of fire, with many studies predicting severe impacts on flora and fauna. We noticed that the word megafire was being used to describe these fires, which got us thinking, what do you mean megafire? We sought to resolve the ambiguity surrounding the meaning of the term megafire by conducting a structured review of the use and definition of the term in several languages in the peer-reviewed scientific literature. We collated definitions and descriptions of megafire and identified criteria frequently invoked to define the term. We recorded the size and location of fires described as megafires, mapping them to reveal variation in size. So what did we find? Here, we see a clear increase in the number of studies that defined, described, or reported a megafire. Continent was assigned to the first author's primary affiliation. At the time of this review, 2022 was incomplete. This figure shows the number and proportion of the various criteria used to define or describe megafire. What we are seeing here is that while there are various descriptors used when defining megafire, fire size is clearly the most common. Here, panel A shows reported wildfires which were termed megafire events and their corresponding size and location, while panel B shows the number of studies which mention a megafire event. So what we see here is that megafire is being reported across many continents with varying wildfire sizes reported as megafire events. In this figure, panel A shows the map of megafire definitions and the location of the first author's primary affiliation. Panel B shows the number of studies that define megafire within various size categories and how this varies according to the lead author's geographical location. We now had enough information to define what megafire is. We used the consensus from peer-reviewed definitions to define megafire as fires over 10,000 hectares arriving from a single or multiple related ignition. We then defined two additional terms, gigafire and terafire, which describes fires over 100,000 hectares and 1 million hectares. Circling back to the first figure I showed you, located on the bottom left of the screen, in a recent response paper to our original 2022 paper, we conducted an updated literature search. We found that the use of megafire has exploded in 2022 and 2023, as shown on the figure on the right. In the response paper, we outlined why abandoning the term is neither practical, possible, nor beneficial. Instead, we argue that consistent usage underpinned by clear definitions is essential. Adopting a clear size-based definition of megafire strengthens clarity and comparability across research and management practices globally. Precision in terminology is crucial for advancing research, improving communication, and informing effective fire management and policy. The next thing we wanted to do was understand how the 2019-2020 wildfires impacted species. We wanted to examine the impacts of fire severity and biodiversity at a landscape scale on species, community and functional diversity, and predator-prey networks. We conducted this study across 5 protected areas in the Upper Murray region of Victoria and New South Wales, shown here in red on the map of Australia. This region has received very little historical species surveys and was a bit of a data shadow. Between December 2019 and February 2020, parts of the study area burned during the Green Valley Fire. This fire was part of a larger gigafire in which 6 fires emerged and burnt over 600,000 hectares. Using fire severity maps, we selected 24 circular study landscapes, each with a diameter of 1 kilometre. In each landscape, we deployed 8 cameras. We employed a whole of landscape design, which is novel for looking at the impact of fire severity. Whole of landscape studies measure landscape properties and biodiversity across replicate landscapes. This matches the scale at which fire generates heterogeneity in landscape structure and ecological communities. Across 24 landscapes, we captured gradients in the extent of areas that burned at high severity, the extent of areas that remained unburned, and fire severity diversity, which is one way that biodiversity can be measured. This study design is highlighted here in the 3 figures, which display the variation captured in the 3 variables in each landscape. We used area proportionate sampling, which meant that the 8 cameras in each landscape were deployed according to the proportion of each burn severity within each landscape. For example, if 50% of the landscape was burnt at high severity and 50% remained unburnt, 4 cameras would be deployed in high severity burnt areas and 4 cameras would be deployed in unburnt areas. This is shown here in the 3 images. This method is much more powerful at drawing conclusions about the impacts of wildfire when compared to other site-based analysis. This method enables us to draw conclusions about species responses to areas with certain amounts of high severity fire, unburned areas, or biodiversity. To get a sense of our study ecosystem after fire, the images here show the effects of fire severity on vegetation and forest structure during various stages of recovery. From left to right, we see an unburned area, an area burnt at high severity 1 month post-fire, an area burnt at low to moderate severity 20 months post-fire, an area burnt at high severity 20 months post-fire. so you can really see the rapid changes in vegetation and cover post-fire. Using wildlife cameras, we surveyed terrestrial species. 192 cameras were deployed across 24 landscapes in October 2021, approximately 20 months after the wildfires. Cameras operated continuously for 358 days. We collected over 2 million images, which contained almost 300,000 wildlife images, leading to more than 38,000 30-minute events. A total of 87 species were identified, including 54 bird, 28 mammal, and 5 reptile species. To test animal activity between landscapes which had very extensive fire severity variables and biodiversity, we fit Bayesian generalized mixed effects models. Additionally, as we had a continuous data set, we were able to divide the data into 3 120-day time periods, enabling us to understand if animal responses changed over time. From the 45 species that we analysed, we found that most species did not respond to fire severity variables. 7 species responded to the extent of high severity fire, 8 species responded to the extent of unburnt areas, and 7 to biodiversity. The figure shown here, where the coefficient and 89% credible interval does not overlap 0, a change was recorded. A positive interaction implies the relationship with the landscape variable is increasing and a negative one the opposite. Generally, native species responses were negative, while introduced species responses were positive. Both European rabbit and Javan deer showed positive responses to fire-disturbed landscapes, particularly in areas with greater amounts of high-severity fire. Responses were often muted at the community level and for predator-prey networks. When examining how these responses changed over time, most species did not respond to fire severity variables. However, there were some common patterns in the species that showed a response. Over time, more species responded to areas with greater amounts of high severity fire, and native species tended to respond negatively, and introduced species tended to respond positively to fire severity variables over time. We predicted species activity from our models and how they changed through time. Shown here are select species which did respond to fire severity variables, notably both European rabbit and Javan deer, along with introduced species richness increased in areas with greater extents of high severity fire. Overall, the impacts of these wildfires on the terrestrial species that we studied in our study region were relatively minor. This suggests resilience among the terrestrial fauna that we studied. One explanation for this widespread resilience is the long-term history of wildfire in the study region. As such, many animal species have evolutionary adaptations to deal with fire. These adaptations range from physiological traits, which enable resilience to varying fire severities, or behavioural strategies that allow species to exploit a range of post-fire habitats. Our findings suggest that certain ecosystems and species which have evolved with wildfire may exhibit a high degree of resilience to variations in the extent of fire severity variables. However, it is possible that the species we study, which are largely widespread, mobile, and terrestrial, are a subset of the broader animal community that might be resilient to wildfire. Several invasive species show positive responses to fire-disturbed landscapes, particularly in areas with greater extents of high-severity fire, suggesting the adaptability to exploit resources in early successional habitats created by fire. As such, this could amplify the ecological impacts on native species through increased herbivory. As many of the species we studied demonstrated resilience from these wildfires without extensive interventions, our findings support the merit of a targeted approach to management plans after wildfire. Our results suggest that fire management does not need to achieve mixed severity fire in our study region for the species that we studied. As landscapes with greater extents of high severity fire tended to have more introduced species driven largely by introduced herbivores, we suggest that interventions that limit herbivore abundance and impacts would focus on areas that burnt at high severity. We then decided that using the camera traps from the previous landscape analysis, we could conduct a site-level analysis on the species responses to the 2019-2020 wildfires. We wanted to examine the impacts of fire severity at a site scale on the activity of animal species, vegetation characteristics, and species dial activity. Here, we again see the same study area. To understand what we did next, it is crucial that I mention in the landscape analysis that I just talked about, our spatial replication was the 24 landscapes with 8 cameras in each, and we were looking at how the extent of fire severity variables and biodiversity affected species. In the next site level analysis, we looked at all 192 cameras as their own spatial replicas, grouping them by fire severity. This answers questions about how fire severity affects species at a site scale, thus limiting the conclusions to species responses to individual fire severity classes. In panel B, you can see examples of 8 sites used in the study. In addition, at 80 sites, we conducted vegetation surveys assessing vegetation structure and composition across different fire severity classes. To test the response of vegetation characteristics and animal activity at sites from different fire severity classes, we fit Bayesian generalized mixed effects models to assess how wildfire and fire severity affects species dial activity. We use generalized additive mixed models. Here, we see the coefficients and credible intervals from the Bayesian models comparing vegetation responses in different fire severity classes compared to unburned areas. Overall, areas subjected to high severity fires had less alive trees and more dead trees, less canopy cover and leaf litter, higher vegetation cover, as well as a greater abundance of logs. Fire severity had a limited effect on the activity of animal species. Greater impact occurred following high severity fire, where 8 of 29 species were affected, compared to 3 of 29 in areas burned at low to moderate severity. However, only 4 of 29 species in high severity areas and 1 of 29 species in low to moderate severity areas responded negatively, demonstrating a general resilience to wildfire. The figure on the right shows the predicted species activity across fire severity classes. Interestingly, our results indicate that areas burned at high severity have higher introduced mammal richness and reduced native mammal diversity. Not satisfied that the site-level manuscript was bound for a low-impact journal simply because it echoed my landscape-scale project results, I began to think beyond relative abundance metrics and investigate if other drivers might be at work, which led me to think about dial activity. Could this be changing in response to wildfire? At the time, no one had tested this, and with such a large data set, it offered an opportunity to do so. The dial activity patterns differed for 7 of 17 species in areas subjected to wildfire. In the figure on the left shows some of the species which did alter their dial activity patterns in response to wildfire. The figure on the right is a difference of smooth plot comparing dial activity patterns of species across fire variables throughout the day. This illustrates temporal periods during which species exhibited differences in activity in response to fire variables. Significant differences occurred where the confidence intervals do not overlap 0. Our findings suggest that fire severity profoundly affects vegetation. Areas burned at high severity had altered canopy cover and plant composition, which caused forests to become younger and smaller in size. Despite these structural changes in vegetation, signs of recovery were common, with fire severity having a limited negative impact on the activity of most animal species we studied. This lack of response suggests that animal species have evolved adaptations to cope with large-scale disturbance, such as large, high-severity fires, which is unsurprising given the high frequency of wildfire in Australia. The differences in terrestrial species dial activity, identified as behavioural plasticity, might be a potential adaptive response to wildfire. The next project was to understand how species survive wildfire, which led us to think about the humble common wombat, whose burrows are one of the few habitat features that can survive fire. During the 2019-2020 wildfires, a viral tweet spread good news about wombats herding fleeing animals into their burrows. Whilst obviously incorrect, our interest in this tweet and the subsequent article in the conversation got us thinking, what could be going on at wombat burrows? Common wombats are the largest burrowing marsupials on Earth. They have a wide distribution indicated on the map in grey. Their habitat was severely impacted by the 2019-2020 wildfires, indicated on the map in red. Wombats excavate complex burrow systems with multiple entrances and chambers, which maintain stable below ground temperatures. Burrow construction creates significant soil turnover, which enriches mounds with nitrogen, promoting higher herb cover. Our objective was to understand the ecological role of common wombat burrows in habitats that burnt at varying severities during these wildfires. This study was conducted in Woolmargama National Park and Woolmargama State Forest, located in New South Wales. During these wildfires, over 51 days, approximately 18,000 hectares of the park burnt at mixed severities. We used wildlife cameras to survey animal activity at 28 site pairs. Each site consisted of a common wombat burrow and a nearby paired control site. Site pairs were from the same fire severity class and comparable habitat, which allowed for the removal of any site-level bias. Cameras were deployed for 16 months. Cameras were deployed 16 months after the wildfires and operated continuously for 10 months. 7 sites were established in 4 different areas, including unburnt areas outside of the fire scar, unburnt areas within the fire scar, low to moderate severity burnt areas, and high severity burnt areas. We spent a lot of time looking at wombat burrows with just over 16,500 trap days. We collected almost 750,000 images, which contained almost 400,000 wildlife images, leading to more than 15,000 30-minute events. A total of 56 species were identified, including 33 bird, 20 mammal, and 3 reptile species. At burrows, 47 species were identified, and 44 at control sites. To test animal activity between burrow and control cameras, we fit Bayesian mixed effects models. To test for compositional differences between species assemblages at burrows and control sites, we used permanovas. To understand the association between body size and burrow use, we compared species weight with their presence at burrow and control cameras. Finally, to examine if the associations were more pronounced in areas that experienced high severity fire, we again used Bayesian models to model response variables as a function of site type and fire severity class. We observed 31 species interacting with burrows. These interactions include inspecting, foraging, entering and emerging, drinking, and bathing. Seen here are some examples of these behaviours: a lace monitor and a grey striped thrush foraging, a redneck wallaby and an echidna inspecting a burrow. We found that burrows periodically filled with water and animals were regularly seen drinking from them. Seen here a swamp wallaby and a pied currawong drink water from a flooded burrow. Here, we see the coefficients and credible intervals from the Bayesian models comparing species activity at burrows versus controls. Below this are examples of species activity predicted from these models. The results indicate that bush rats, agile antechinus, lace monitors, painted button quails, grey shrike thrush, house mice, and black rats exhibited increased activity around burrows. On the other hand, swamp wallabies, redneck wallabies, eastern grey kangaroos, Australian magpies, satin bowerbirds, crimson rosellas, white-winged chops, and feral pigs showed higher activity at control sites. We also found that burrows had greater native mammal richness and total richness compared to control sites. Here, we have the differences in species composition at burrows and control sites. Burrows were associated with species such as agile antechinus, bush rats, lace monitors, white-throated tree creepers, and black rats, while control sites had indicated species such as redneck wallabies, eastern grey kangaroos, and feral pigs. Here, we fitted a linear regression of the effect sizes of the credible intervals from our Bayesian models against the natural logarithm of body mass for mammals. Our findings suggest that small mammal species exhibited a positive association with burrows, while larger mammal species showed a negative association. This size-dependent relationship was specific to mammals and was supported by a strong negative relationship between effect size and body mass. Here, we have the coefficients and credible intervals from Bayesian models comparing the activity at burrows versus control sites in various fire severity classes. Below this are examples of species activity at different fire severities predicted from our Bayesian models. Associations between species and burrows persisted and strengthened in fire-impacted areas, especially in high severity burn areas. Smaller sized animals, including agile antechinus, bush rats, and painted button quails, exhibited positive associations with burrows in high severity burnt areas, displaying increased activity. Mammal richness was higher at burrows that burnt at high severity, indicating a positive correlation between fire severity and the presence of mammals. Understanding the role of common wombat burrows was not known, and our research was the first to do this with control cameras. We demonstrated that the ecological facilitation by common wombat burrows positively impacts native species activity and richness, influencing community composition. We found that body size determines mammalian associations with burrows, with smaller species being more active and larger species being less active around burrows. Common wombats are large-bodied and stocky mammals, which are known to compete with macropods for resources. So it is plausible that common wombats actively deter larger competitors away from their burrows, or that macropods avoid burrows to reduce the risk of a negative encounter. Interestingly, the associations between some of the species and burrows persisted and strengthened after high-severity fire, indicating burrows offer some form of post-fire refuge. For small vertebrates that are vulnerable to predators, many flammable refuges such as logs or hollows are consumed by severe fire. Wombat burrows survive fire and can persist for decades, potentially providing important post-fire refuge. These findings reveal that the relationship between burrows during disturbance events, highlighting the importance of burrows as refuges and their role in shaping ecosystems. Our findings shed light on the valuable contribution of common wombat burrows in Australia's fire-prone forests. Our research has shown that common wombats play a vital role as ecosystem engineers, providing resources for other species. The importance of ecosystem engineers for providing crucial shelter for other species highlights an often overlooked risk of co-extinctions due to the loss or continued decline of burrowing species. The value of burrowing species as providers of shelter and refuge likely increases after disturbances across a range of ecosystems. As such, burrowing species, including wombats, play an underappreciated role providing shelter and refuge, especially in burnt areas where post-fire resources are low. A bit of a shameless self-plug here. This paper was published in 2024 and was well received in the public space. It was published in more than 140 news agencies globally. However, the highlight from this research was that it was published in a cartoon by the first dog on the moon. So where to next? Using my own data set that I've discussed today, we wanted to know if fire severity compresses the spatiotemporal niche of species, like it does with human disturbance. Preliminary results suggest it does, which would be a novel result for fire ecology. During the wombat paper, we decided that a global review of burrowing species, which would provide resources for other species, was needed. And in the months following my PhD, I decided to conduct a narrative review of the topic. In the Nature paper that I mentioned at the start of this talk, we found that frequent historical fire led to greater negative and positive impacts. We now want to know what might be driving those patterns. Could it be species that like or dislike frequent fire? What I'm most excited about with the WildObs dataset is looking at a multi-species continental longitudinal analysis to assess species trends, identifying where species are increasing or decreasing. Additionally, I want to examine how drought, Rainfall, frequent fire, and other covariates drive year-to-year fluctuations in species occupancy and abundance, testing whether conservation areas offer those responses. Thanks to everyone who has made this research possible, and thank you for coming along to my talk.
Thanks, Grant. Does anybody have any questions that they'd like to ask?
Thank you, that was super interesting. I have what might be like a silly question, but like looking at that graph of all the species association with wombat burrows, what did you look at, like where are wombats? Like what is the order of magnitude more than all of those species do wombats associate with wombat burrows?
The reason I didn't do that is because the question was what other species are using wombat burrows. So yes, I have a whole bunch of data. All of the burrows were active. Wombats were seen at all of them. So yeah, I do have all this data on wombats, what time they were active, what they're doing. I did analyze this, and like the landscapes and site paper results, they don't really care about fire. They don't change their dial activity, and the reason, I'm not going to do anything about data.
I'm just kind of curious because you're thinking about like it just kind of in my mind, I was curious as to like how much are these animals spending time there, and for me the easy comparison point would be like compared to a wombat.
Yeah.
But I'm super interested.
Yeah, that's a good point. I can say that the wombats are obviously there, probably the most. There's a lot of wombat photos, which is nice.
I was wondering, so around the wombat burrows, is it the same individuals you think that keep coming back, or is there a good quick turnover?
Yeah, that's a good question. From like you can't obviously ID them, but I mean to a point you can. I can see that this one is big and this one is small, so you get a sense of what they're doing. So from what I understand, looking at all these photos, they sort of come in and use a burrow for a particular period of time. It was always easier to see mothers and offspring. Like they would definitely come in for a few days, maybe even a week, then move on. Other individuals will come to the entrance of the burrow, sometimes have a sniff and leave, sometimes have a sniff and then the other wombat will come to the entrance and they're off. So yeah, they seem to be using something like a network of burrows where they will rock up for just a short period of time is what it looks like.
I'll take a question here. With large scale disturbances like the 2019-20 bushfires, it's hard to get out and measure impacts immediately. So how was fire measured in your studies?
Fire severity.
Yeah, like did you go out and measure, like inspect the fire at each site?
Yeah,
you had those great maps of the fire severity.
Yeah. So I probably should have said fire severity classes were ground truth. So whenever I put a camera out, it had to match my assessment of what my fire severity map said. So like it goes off canopy cover really. Is it completely consumed? Is it partially consumed? And stuff like that. So
great talk, super interesting. Some of the studies with fire severity use baited camera traps, is that right?
yeah, so the landscape and site projects use baited cameras and wombats were not baited. Yeah.
With the baited camera, the detectability of something coming to the camera trap is going to be the same between any of the habitats, right? Because it's right in front of it, it's just shooting at whatever comes to that. Is the detectability of the bait the same in different fire habitats, like unburnt versus burnt?
I mean, I didn't test it. I think because everything was baited across my 192 sites, sort of assumed that the effect of the bait is sort of the same blanket, but whether bait is better at pulling in animals or attracting animals in an unburnt site where the canopy, the mid-story and ground story is a little bit more open, then the high severity sites is probably in question.
Or less food?
Yeah, I mean, it could be that, yeah, but I did the test.
kind of working into a question rather than a comment, but I'm just quite, like, I was really surprised at the limited effect of extensive severe fire, you know, compared to other groups where you tend to see more of an effect, particularly, you know, the role of, I'm thinking of the role of long unburnt. So your unburnt class, was that long unburnt or was it just not burnt in that immediate
Not burnt
recent
in
fire?
that fire.
So it could have been burnt quite recently, but just not like in the last 5 years, but not in that fire.
Probably not, I would have put, like, yeah, I don't think I would have, I mean, I know I didn't put out cameras that in sites that would look like they were burnt quite recently, and I know the study area hadn't had a bit of a fire through it, they had like management burns and stuff like that, which I avoided, so I didn't put up cameras in areas that had been burnt. It's quite obvious when you walk through a system like this burnt 5 years ago, it's super thick.
So what would you estimate is the sort of minimum time since fire in the unburnt areas?
Good question. I don't know, but I can go and I have all the historical fire maps. These were included as testing my memory here, something in my landscape paper. But yes, I did look at the role. It was one of my covariates, was the amount or the diversity of historical fire within my landscapes was accounted for. But I suppose that doesn't really answer your question.
Yeah, because I'm just thinking about, you know, so from a time since fire perspective, usually that's quite influential with long unburnt stuff.
Yep.
But that probably, if that was happening here, maybe it wouldn't necessarily have come through, and that was the focus, obviously. But it always interests me because, you know, it's, you know, your general conclusion being that maybe there wasn't some really big fire severity driver for your mammals or what species you could detect, primarily mammals. But, you know, it only takes a few, because the thing is you can make burnt stuff, you can't make long unburnt stuff. So there's, you know, in your communications to managers about this, you know, how do you sort of pitch that? Because I noticed in the talk you're very careful about it, this relates to our area, the species we're studying and stuff. You know, did you feel the need, given how contentious this topic can be, you know, how did you go about communicating that nuance?
I mean, I don't know, communicate with anyone, I just published the paper. Yeah, look, you raise a good point, but I do know that I was quite careful in selecting my unburnt areas and ground truthing everything. So like there were sites where I'm like, oh, I'm gonna put my cameras here. It looks a bit different to my other unburnt areas and stuff like that. So the same way I was careful about the low and moderate and high severity sites, I chose my unburnt sites relatively carefully to ensure, like some of them were outside of the parks, like two of mine, Burrow Pine Mountain and Jingellic, they completely burnt, like the whole park burnt. So my unburnt controls are in quite a nearby, like within 20 kilometres or something, another unburnt national park. Whereas Wilmargam are roughly half burnt, 70% burnt. So I had my controls within that. So yeah, it's a good question though, but I think considering Don's nature paper found similar responses where like certain species overall were affected if they were, you know, sat up in frequent fire or drought or they were outside of conservation areas. But overall the sense was a lot of these species that are at least detected, like for me it was on camera traps, which is just going to be common mammal species in the end. That's all I saw. I thought I was going to see quolls or something like that. I saw nothing.
No quolls at all.
No.
Because I was wondering what was in that amazing treasure trove of images.
Yeah, there's a lot of images, and the quoll thing drove me. I used it as a motivator every day. Like, I'm definitely going to see one today. I didn't see one. I just saw heaps and heaps of macropods. But yeah, so the things I studied, I think that I'm relatively sure of what we concluded. That the species in these parks, just like that I studied, just didn't stuff about fire. I don't think.
Fascinating.
Yeah.
Really neat piece of work and really neatly put together pieces too.
Oh, thank you.
Grant, do you think there's anything specific about wombat burrows, or is it just for those small mammals that are responsible? Is it just a subterranean structure, or is there something? Well, I think about this in terms of management.
Yeah, no, it's a great question, and Dale has an honours student from co-supervising that is testing this at the moment with like giving up densities. My personal feeling is that the small mammals are coming there for food. The burrows are often wet, not just with pooled water, but often damp in the ecosystem that I was in. And it seems to bring a lot of insects in. This was something I sort of speculated at the start, and I was told to go and, if you want to go test it, go and do it. I didn't, because I just want to do insect stuff. It's a bit too much time. And so I think the small mammals are coming in for food. The lace monitors are coming in to eat stuff. They often, I would see scratch marks on the side of the entrance walls going into the burrow. And a few times I captured them pulling this out. I think they're getting, there's the white-throated tree creepers, there's a few birds that continually go into the burrow. So I wouldn't be surprised if something like this, I'm not 100% sure, but the lace monitors are rocking up in the day and clearly looking for food. A few times they go in and come out, or they just come out. Whether the camera missed that, I'm not sure, or whether then they went out another exit, I'm not sure. But yeah, I think Dale was following up with some questions there as to what is driving that for the small animals. Because a lot of the time, actually, black rats were quite often seen with young, or sometimes seen with young, going in and out, and quite young, like pups, not sure. So yeah, there's definitely some of the species are coming in there for food, maybe like staying overnight, I'm not sure, but yeah, they're definitely very active in this. And like,
Do you think we'd ever get to a stage of creating burrows as a fire refuge in these landscapes?
Another one of Dale's honours student is writing it, well, she's finished, but she is writing this up now. So she looked at, not in this ecosystem, but the role of artificial refuge being burrows. So she tested different types of burrows. One was made out of metal, I think, and one was something else, and how that attracts animals. So she really just did the same project in a different, she was in the desert, is in Mali somewhere. So yes, I think there is scope for looking at whether artificial refuge or burrows can play a similar role. I suggest they might. It just depends what the species are using the burrows for, because if it's not just I suppose a space to rest and shelter, if it's food, perhaps an artificial burrow doesn't, generate food resources like a wombat burrow would.
Yeah.
So you said that when the owner of the burrow would turn up, the animals that were there would leave. Is that right? So that's the opposite of what was being claimed that wombats were hurting them.
Yeah, no, I think
very happy about it.
I think I just speculated that perhaps wombats could be causing larger bodied animals to not come around the burrows. But yeah, the herding thing is definitely not happening. Can confirm. But yeah, to be honest, I think it's, you can't really say that. It would be very interesting to know and very hard to test that if during a wildfire event, I suspect a lot of these species, if they are lucky enough to come across a burrow as you're fleeing a wildfire, they might head straight down. But unfortunately, I didn't test that. I looked at what they're doing after the fires, but yeah. Sorry, I can't answer your question.
But it'd be doable though, wouldn't it, if you had controlled birds?
Yes, it would, and then you didn't care about your cameras.
Yeah.
Yeah, and then you want to be able to get your data back, so if they're, yes, but I mean, you could probably do it even with, smoke or some sort of fire stimulus.
Yeah.
It would be hard to do in the field, but yeah, I think someone should probably test that. I think there's a lot of scope for looking at what is using other species burrows in Australia, because it's really well studied around the world. I did this narrative review on the topic, and there's a million examples of other species using like aardvark burrows and all different stuff. But yeah, some of this burrowing species in Australia, I think I'd like to have a look at what uses burrowing beton burrows with the same setup, a camera and a control camera. How to get them in a outside of a reserve is a little bit hard. I think they're on a couple of islands of Western Australia, but I think that's a question which warrants answering just because of the length of time that burrowing betons burrows will persist in the landscape. I think some of them, I think I read somewhere years ago during my honours that some of them persist for 100 years and rabbits are now using these same burrowing beton systems. Obviously they're not there anymore, but yeah, I think that would be interesting, especially more interesting than the bilby stuff, because the bilby seem to be a bit more transient. They'll come and use this one and they go over there, whereas the betons build these big networks, underground tunnels. I think there'd be heaps using this.
Questions online?
For the list of species that either does or does not well, if you look at some of the traits of the species and the traits of the ecosystem post the fire, so I would imagine animals that like fresh growth, they could be drawn to a place of fire afterwards, and they would be driven out again.
I think you're right, and I didn't test this. So I got nothing. I'm sorry, but that is a good question for sure. I think someone might be doing this with Don's the nature paper. Someone that I know is looking at the traits, looking at much bigger data set than what I have. So they'll probably answer that question in a better way than my small data set could.
If there are no more questions, we can all thank Grant for answering.